Right. So I would like to begin by thanking the organizers for inviting me to speak and also for moving this conference online, which actually gives me the chance to be here because, yeah, I was not going to be able to travel to Michigan, but it's really wonderful to be here online. So what I'm going to talk about is Grassmannian categories of infinite rank. This is joint work with Jenny August, Mandy Chang, Eleanor Faber, and Sarah Gratz. And in fact, it comes out of a woman in non-commutative algebra and representation theory meeting that was held in Leeds in May 2019. So what was our idea? So the idea is to categorify Grassmannian cluster algebras of infinite rank very similarly to the categorifications we have seen in the talks by Alistair and Karen. Though, yeah, we are going to approach it by generalizing or letting n tend towards infinity, and I'll explain that in a minute. So that was the goal we have. If you look very closely, then maybe you'll spot that we call them Grassmannian categories and not Grassmannian cluster categories, which is work in progress, and we hope to be able to say more. But effectively, we define some categories and they are closely linked to the Grassmannians, but so far we have not been able to define, for example, a cluster character, as Alistair has explained that he and in the joint work with Jensen and Sue has defined. Right, okay, so I guess cluster algebras in the title, so I probably don't have to say a whole lot about them. Everybody knows cluster algebra is a subalgebra of the ring of Laurent polynomials, and it's given by generators, which are the cluster variables, and they come in clusters, and by mutation of clusters we generate the whole cluster algebra. And instead of giving a precise definition of cluster algebras, I will give an example, namely the Grassmannian cluster algebras of finite rank. So if we denote by GRKN, the Grassmannian of K subspaces of Cn, then for K equal to 2, already Fuhrman and Zelewinsky in their original paper showed that the coordinate ring of that Grassmannian has the structure of a cluster algebra. And then Jean Scott showed that this is true for any K. And so if we look at the Plücker embedding and look at the polynomial ring in the Plücker coordinates, that is we can consider this as variables which are indexed by K subsets of the set 1 to n and mod out by the ideal generated by the Plücker relations, where the Plücker relations are given as follows. So I have tried to describe them. So basically, it's an alternating sum of products of two Plücker variables, where for a subset J and a subset J prime of this set n, which is simply the short notation for the set of integers 1 to n, such that J has size K plus 1 and J prime size K minus 1, then we look at all possible ways of removing one element from J and adding it to J prime. So we have two Plücker coordinates or indexed by subsets of size K. So somehow this is the structure we're interested in. And then we want to sort of say how these Plücker coordinates are related to the cluster structure. And in order to do that, let's first define what we mean by crossing K subsets and then by compatible Plücker coordinates. So for I and J, two K subsets of Z, then we call these two K subsets crossing if there are two integers I1 and I2 in I which are not in J, and two integers J1, J2 which are J in J but not in I, such that we have I1 less than J1 less than I2 less than J2, or the other one where we start with J1. So this is when the two K subsets are crossing. Of course, if they're not crossing, we call them non-crossing. And we say that two Plico coordinates which are indexed by these subsets I and J are compatible if the corresponding K subsets are non-crossing. Okay, so this definition of compatible, G and Scott showed that maximal sets of compatible Plico coordinates are clusters. And in general, for K greater than 2, these are not all the clusters. They're more clusters than they are maximal sets of compatible Plico coordinates. But if K is equal to 2, then the Plico coordinates are in one-to-one correspondence with the cluster variables. The maximal sets of compatible Plico coordinates are exactly the clusters, and the exchange formulas are given by the Plico relations. Okay, so here's a slightly different point of view, but we have sort of seen it, of this categorification of the Grassmannian cluster algebras of finite rank by Jensen, King, and Su. Namely, they consider the polynomial ring in two variables and mod out by the ideal generated by the relation xk minus y to the power of n minus k. So this is a plane curve singularity. And on this ring, we have an action of the cyclic group in n elements, which we can consider as a subgroup of SL2C, and which acts on the polynomial ring by sending x to psi x and y to psi inverse of y for an element psi in the cyclic group. Given this, then the categorification of these of the coordinate ring of the Grassmannian that Jensen, King, and Su give is the mu-n equivariant maximal Cohen-Macaulay Rn modules. And they sort of very precisely describe the correspondence in the cluster category with the different properties of the cluster algebras. Well, namely, so this Rn is a Gorenstein ring, so we have a Frobenius category, and they show that the rank 1 modules are in bijection with the Plico coordinates. So for each K subset of 1 to n, we get a rank 1 module. And this bijection is structure preserving in the sense that if we have two compatible Plico coordinates, that is non-crossing K subsets, then the extension space between the corresponding rank 1 modules is 0. And here I have written it in one direction, but of course we also have x1 mj, mi should be 0. Furthermore, they show that this category has cluster tilting subcategories, and they are in bijective correspondence with the maximal sets of compatible Plico coordinates. And finally, as Alistair described, they define a cluster character. So this is a map from the category into the cluster algebra. Which has certain properties. For example, it takes a direct sum to the multiplication of two modules to the direct sum to the multiplication of the two cluster characters, and it's compatible with exchange triangles or sequences in this Frobenius category. And they define this cluster character using the categorification of the affine open cell of the Grassmannian via a subcategory of the preprojective algebra of type A by Geis, Leclerc, and Schroll. So somehow this is the situation for the finite rank Grassmannian cluster algebras and Grassmannian cluster categories. And this is what we want to generalize to the infinite case. So let's maybe first look at what the Grassmannian cluster algebras of infinite rank are. So as a definition, we simply said that AK should be the ring which is generated or which is indexed by all possible K subsets of Z. And we mod out by the Plücke relations just as before. So we take subsets of size K plus 1 and K minus 1, and we take the alternating sum of removing elements from the bigger one and multiplying the two Plücke coordinates together. Then Grabowski and Graz showed in 2014 that this algebra can be endowed with the structure of an infinite rank cluster algebra, and this can be done in uncountably many ways. So you start with a certain cluster, and then you take finite mutation sequences, and starting with different seeds, you get different cluster structures. And then Sierra Graz in 2015 showed that this algebra is the co-limit of cluster algebras of finite rank in the category of rooted cluster algebras. So somehow, because somehow everything depends on what seed you start with, you have to sort of place yourself in the category of rooted cluster algebras, where you have a cluster algebra and you fix a seed, and then for this fixed seed, one can show that AK is the limit of these finite rank cluster algebras. And as an appendix to their 2014 paper, Michael Gröchening showed that this AK is actually the coordinate ring of a Grassmannian of infinite rank. He did it for the case K equal to 2 explicitly, in that he showed that that AK is the homogeneous coordinate ring of the Grassmannian given by two-dimensional subspaces of a pro-finite dimensional topological vector space, and this then can be generalized to any K, the construction he gives. So this is what we would like to give a categorification of. And what is the idea? Well, the idea, of course, is that in JRKN, we let n tend towards infinity, and this is precisely the construction of Gröchening, where we consider K subspaces in an infinite or profinite dimensional vector space. And if we consider this relation categorifying the cluster, the Grassmannian categories of finite rank by Jensen, King, and Su in a neighborhood of 0, then this term y to the power of n minus k will tend to 0, and we're simply left with xk. And this is sort of the ring we take. So this is the Gorenstein ring. And if we now have n tending to infinity, then when before, for the finite case, we had an action of a cyclic group on the polynomial ring. Well, if n tends towards infinity, then somehow that cyclic group becomes really the group of invertible elements of C, so C star or GM. And it acts in the same way. If we take a psi in that group, then it acts on X by multiplication with psi, and on Y by multiplication with psi inverse. And the category we proposed to be the Grassmannian category of infinite rank is the category of GM equivariant maximal Cohen-Macaulay modules over this hypersurface singularity R, which is a polynomial ring divided out by x to the power of k. So working with these GM equivariant modules is not always so easy. So we make use of the fact that the character group of GM is isomorphic to Z, which induces an equivalence of the category of finitely generated GM equivariant R modules and the category of finitely generated Z-graded R modules, which implies that the category here we defined of GM equivariant maximal Cohen-Macaulay modules is equivalent to the category of Z-graded maximal Cohen-Macaulay R modules. And this is really the category we're going to continue working with. Okay, so our aim really was to show that this is an additive categorification of these Grassmannian cluster algebras of infinite rank. And for that, well, before I say what we can do, let's maybe take stock and see what we know about this category and why we think this is really a good choice for that. Okay, so first of all, R is Gorenstein, so we have a Frobenius category. Of course, by Buchwald's, we know that the stable category is isomorphic to the singularity category of the graded R module. So this doesn't really tell us a lot. It just gives us a different description of the stable category of our category. But if we set K equal to 2, then there's a link with the work of Holm and Jorgensen. Namely, what did they do? So they considered the polynomial ring in one variable as a differential graded algebra with 0 differential and where they place y in degree -1. And then they consider the derived category with finite homology of this differential graded algebra, and they show that this has cluster combinatorics of type A, or actually type A infinity. So somehow the cluster structure of this category is described by triangulations of an infinitygon. And right, so what is then the link of this category with our category MCMZR? Well, if we take a subcategory of our category for K equal to 2, which is generated but by what is called generically free rank 1 modules, and I'll define what they are precisely in a moment. But if we take that subcategory, then the stable category is equivalent exactly to this Holm-Jorgensen category. So somehow, if we disregard the infinite things in some sense, well, a certain sense, and you'll see at the end of the talk what I mean by that, then we get exactly the Holm-Jorgensen category. So this is the first indication that this is maybe a good category. But a very recent paper by Yildirim and Paquette from June 2020 makes this sort of actually even better. Namely, they consider the completion of the discrete cluster categories of infinite type by Iguza and Todorov. So basically, one way of visualizing these Iguza-Todorov categories is by triangulations of a disk where we have finitely many accumulation points. And then Yildirim and Paquette complete that category. And it turns out, and for this completion, they do a lot. They define, for example, a cluster character, which shows that actually they really have a categorification as a cluster algebra. And if we set in our category K2, and if Yildirim and Paquette consider instead of many accumulation points a single accumulation point, then this Yildirim-Paquette completion is equivalent to exactly the category we are considering, namely the Z-graded maximal Kolmogorov modules over the hypersurface singularity for K equal to 2. So these are all good indications that this is a good category to consider. Maybe I should say, oh yeah, I should have maybe said before, what is really nice in the Jensen, King and Su paper, where here we are. So they give the categorification via these plane curve singularities, and these plane curve singularities have an ADE classification, and which is given by certain values of K and N. So for example, K equal to 2 corresponds to type A, and so on. And this numerology, that's what Jensen, King and Su actually already say in their paper, corresponds exactly to the cluster algebras of finite type, which also have an ADE classification, and it's the same numbers of K and N. So that's very nice in their result and work. And if we go back to here, so here in the case K, oops, sorry. obviously pressed something I shouldn't have. In this case, k equal to 2, sort of this niceness sort of persists in the infinite case, in that this category here is of countable Cohen-Macaulay type, which is somehow the best situation we can hope for. But in general, if we look at this category MCMZR for k greater than 2, we are in wild Cohen-Macaulay type. So things are very difficult to describe, and which is why we did what we did. Okay, so what are generically free modules? We consider the total ring of fractions of our ring R, which is, oh, I should have, there's a typo here, so this should be y to the power of plus or minus 1, because it's the localization at the non-zero divisors of our ring R. And then we define a module M in our category to be generically free of rank n if, when we tensor M over R with F, we obtain a graded free F module of rank n. Okay, so now we want to describe the generically free modules, and here's what we can say. So if M is generically free, then M is a syzygy of some finite dimensional graded R module. So we know that all generically free modules are syzygies. And then we have a characterization of the generically free modules of rank 1. Namely, M is generically free of rank 1 if and only if M is a graded ideal of R, which contains a power of Y. And so this gives a good description, especially if we put it together with the third property, namely that every homogeneous ideal I of R can be generated by monomials. And if we put these three properties together, we get a complete picture of what these generically free rank 1 modules are. And the reason we want them, if you think back to the Jensen-King-Su situation, the rank 1 modules are the ones that corresponded to the Plico coordinates. And the analog of the rank 1 modules in the infinite case are the generically free rank 1 modules, and that's why we want a good description of these modules. And so the description we obtain from the proposition is that a generically free rank 1 module is an ideal which is generated by the monomials x to the power of k minus 1, x to the power of k minus 2, y to the power of I1, up down to y to the power of I k minus 1. So we have our power of y in here. And then, of course, since we're in a graded situation, we shift by some integer ik. Okay, so this is maybe not very explicit and a bit confusing, but there's a schematic view of a rank 1 module. And I think probably for you, this is very small. I don't know if I can make it bigger. Did this make it bigger? Okay, so how is that description given? Well, so what we do, in the top line, we have xk minus 1 everywhere. And then going from right to left, we multiply by y. And going from the bottom to the top, we start with y to the power of ik minus 1. And here, and well, we have the different y's, and going up, we multiply by x. And I have grouped things together in such a way that elements of the same degree are in the same column. And what I have written in blue above each column are the degrees in which the elements sit. So for example, x to the power of k minus 1, well, x is in degree 1 and y in degree minus 1. I should have probably added this. So if we have x to the power of k minus 1, we're in degree k minus 1, but then we shift by ik, and we have cohomological degree, so we have to take away minus k. And then if we multiply by y, that means we go down 1 in the degree, so we get a minus 1 and so on. So this is the schematic presentation of this rank 1 module. And what is important is this degree sequence which is written in blue, and I have written it here as the Li and just recorded this degree sequence, and it is a strictly non-decreasing sequence. And we use this description to then show that we get a bijection as we would like between the generically free rank 1 modules and the Plücker coordinates. And if we have a generically free module, we associate to it the Plücker coordinate indexed by its degree sequence. And vice versa, if we start with any K subset, we explicitly can construct the generically free module such that the degree sequence is exactly that sequence. So this is a good start, but more importantly, this bijection again is structure preserving, just as in the Jensen, King, and Su case. Namely, we show that if we have two modules I and j with degree sequences Li and Lj, then the corresponding Plücker coordinates are compatible. That is, the two K subsets given by the degree sequences are non-crossing if and only if the corresponding extension spaces are 0. And then automatically it follows from this description that generically free rank 1 modules are rigid, so they don't have any self-extensions. Okay, so in order to show that this is true, we developed this new combinatorial tool of staircase passes. And for that, I wanted to briefly give you an idea of the proof. Namely, the first step we have to do is we have to remember, how do we calculate extensions? Well, if we are given a module I, we first take a projective resolution, then we apply the Hom functor with in the first variable with the second variable, and that gives us a sequence, and then the cohomology of that sequence gives us the extension groups. Okay, so here in our situation, we have a graded projective presentation which is provided by the matrix factorization of our generically free module. And then to that we apply the graded Hom functor, since we're in the graded situation. And we note that if we have our ring R that's shifted by M and take the homomorphism from Rm to Jm, then we just get a shift of the ideal by minus M that we started with. And this then gives us a sequence. So this is a contravariant functor, so we reverse the M and the N. And the J is a direct sum of appropriately shifted copies of J. So this is what we obtain by applying the Hom functor to this sequence. And then by definition, the X1 between I and J is the kernel of MT over the image of NT. But since we're in the graded case, we're only interested in the degree 0 component of this space. And of course, this is the same as the quotient of the degree 0 components. Okay, so once we have that, we just do a little bit of linear algebra. Namely, okay, so in order to prove that the extension space is 0, of course, it's enough to show that the dimension is 0. So we really are interested in the dimension. And then the dimension, of course, is the dimension of the kernel minus the dimension of the image. But these degree 0 components are actually finite dimensional. So we can apply the rank nullity theorem and express the dimension of the kernel in terms of the dimension of the space minus the dimension of the image, and vice versa, the dimension of the image in terms of the space minus the dimension of the kernel. Okay, so the advantage of that is that we can actually calculate these quantities here. So these 4 quantities here, because the dimension of the degree 0 component of these shifted copies of the ideal J is given by the intersection of the 2 degree sequences. And by that, I mean, we have 2 K subsets and we count how many elements they have in common. And that describes, it's actually the dimension of the space. And then the dimension of the image space of the transpose of M is given by k minus some number beta Lij, and the dimension of the kernel of the transpose of n is given by some number alpha Lij. And if we put these numbers all together, then we get that a closed formula for the dimension of the x1, which is in terms of alpha, beta, k, and this intersection. Okay, so how do we calculate the alpha and the beta? And I would like to sort of show that by an example where I calculate, oops, maybe make it a bit smaller here, these numbers. So we introduced this tool called staircase path, which served to compare two k subsets. So we want to calculate the dimension of x, where I is the ideal down here. So it's x squared, xy, y to the power of 6, and we shift by -1. And j is this ideal here. Then the degree sequence of I is given by -5, 1, 3, and the degree sequence of j is 0, 1, 4. And just for convenience, I label the elements of Li by L1 to L3 and call it L, and Lj is M1 to M3 and I call it M. Okay, and now in a k by k grid, so here k is equal to 3, I simply compare the entries. Okay, so I have L1 less than M1, L1 is less than M2, L1 is less than M3, sorry, and so on. And then I introduce two paths, ALM and BLM, where ALM is sort of has above it all the entries such that Li is less or equal to Mj. And BLM is a path that has above it all the entries that Li is strictly less than Mj. And so we get these two staircase paths, and then the number alpha LM simply counts the number of diagonals which lie strictly above ALM. So ALM is the green one here. And then we count the number of diagonals. So we have one diagonal, a second diagonal, and a third diagonal. So the number is 3. And then beta LM is the number of diagonals strictly below the BLM path. Well, that's the red one here, and there are exactly 2 lying below. Okay, and then if we compare the two sets L and M, well, they have the number 1 in common, so the intersection is equal to 1, and therefore the dimension of the extension space is alpha, so 3 plus beta, which is 2, minus k, which is 3, minus 1, which is the intersection, so we get dimension 1. And if you check, then you find that this is good, because we want these corresponding k subsets to be crossing, and they are. Okay, so this is what we can say in the general case. In the case k equal to 2, we can say a little bit more. So if k is equal to 2, then we're in this case that I briefly touched on before, where our category coincides with the completion of Yildirim and Paquette, and we can describe all the indecomposable modules. Namely, they correspond on the one hand side to the generically free modules, which are of this form we have seen before, which in the case k equal to 2 are simply the ideals x and y to the power of k and their shifts, and they correspond to this tiny finger picture you can see here. But they can also be represented by arcs in a circle, which has, I have indicated 0 here, and it has 1 accumulation point. So you can think of this round point here as infinity. So the generically free modules correspond to finite arcs. And then the other set of indecomposables we have in this category are shifted copies of the polynomial ring in Y. And they correspond to arcs that start at the number L, where L is by what we shift, or minus by what we shift, and then they go towards infinity. And in this case, okay, so we know that when two crossing, I mean, two subsets are non-crossing exactly if the corresponding finite arcs don't cross. And in that case, we have already seen that the x1 is 0, but the same is actually true for the infinite ones, with the slight caveat that we have actually 0 also, one more 0 crossing it, because we have sort of extensions only in one direction. But here we can actually say that the dimension of the x1 is either 0 and 1, and it's 1 exactly if the two arcs cross. And for two infinite arcs, they might cross at infinity. But then we only have extensions from left to right. So somehow from the smaller one. So if we had a second arc here to this one. Okay, so this is a complete description of the indecomposables, and that's very helpful because this is the first step to describing cluster tilting subcategory. The second step to describe cluster tilting subcategory is to be able to give a complete description of the Hom spaces between indecomposables. And in this case, k equal to 2, we're able to do that. And this allows us to show that this category of this Grassmannian category, or this Grassmannian cluster category, has cluster tilting subcategories, and they are of the form of this form here. So we have one arc going towards infinity, and then we have, I guess, what often is described as a fountain, and this sort of source of the fountain can be any integer, and they correspond precisely to clusters in the cluster algebra. So this really gives a complete description of this correspondence, or this between cluster category and cluster algebra. And we're hoping to be able to do something similar for the general K case, but of course things are much more complicated because we have wild Cohen-Macaulay type. Thank you.
Thank you very much. Let's thank our speaker for a nice talk. And let's see, I'll turn off the recording.